This seems crazy. Why again does this work?
That pressure is really intense.
The Curiosity rover, a $2 billion gamble that worked. Now, Curiosity is roving Mars, discovering a past very different than today.
We found ingredients for life.
We're working with a multi-billion-dollar rover. We have to make sure that nothing goes wrong.
We can see some dents in the right middle wheel.
The wheels are showing a lot more damage than we expected.
Ah, okay, that's interesting.
And then one day, the drill did not execute as commanded.
We didn't know if we'd ever be able to drill on the surface of Mars again.
Man, when the whole mission is riding on that, it's tough.
But there are some days when you just sit back and you realize, oh my goodness, this is Mars. And that just kind of blows your mind.
In late 2017, Curiosity surveys Gale Crater, its home since 2012. On the horizon, the crater rim, and down below, the rover's 11-mile trek from its landing site to this mountainside 1,000 feet above the crater floor. Curiosity found that this crater once held freshwater lakes for tens of millions of years, with all the ingredients for life. It's been a productive but difficult journey, and it began long before Curiosity landed on Mars.
Back in 2006, we were called to NASA headquarters. The event involves a whole bunch of top brass, including the NASA administrator. The room is full. The other centers are all live. Everyone's milling about nervously.
Adam Stelzner is an engineer from NASA's Jet Propulsion Laboratory. In 2004, he was part of the team that landed the rover's Spirit and Opportunity on Mars inside airbag cocoons. But they'll need something radically different for the next mission. A much bigger, heavier rover they call Mars Science Laboratory, also known as Curiosity.
And I had to present this arguably crazy-looking plan to land this huge rover on the surface of Mars. So it was a little scary. So Martian entry, descent, and landing. It's about energy control. It's got 4 basic components, and that goes for any Mars EDL.
It's the most dangerous phase of any mission to Mars, arriving at 13,000 miles an hour. And on the ground just minutes later, with no help from anyone on Earth. They call it 7 minutes of terror.
.99% of the velocity comes out in the entry phase, where we dissipate the energy to the Martian atmosphere.
It all happens faster than the time it takes to send one radio command from Earth. So every step is pre-programmed.
The parachute slows us down from 1,000 meters a second to about 100 meters a second.
So far, it looks like a typical Mars entry. But now comes something new.
Then we separate out of the back shell and go into a powered descent mode. We descend for the last 2 kilometers, look at the ground with the radar, and then about 20 meters from the surface, we employ our touchdown system, which is called the Sky Crane. We deploy the rover. We're still maintaining a constant vertical velocity. We touch down, cut the rover free, and fly off. It is a new architecture, and frankly, it looks crazy. It looked weird. It looked scary. Very crazy, wacky thing. And it looked like that to the folks at NASA headquarters. And so we went through what ended up being close to 2 hours. There's lots of questions, there's probing, legged landers a la Viking, and the rover. But you could watch the room sort of come around. And by the end of the presentation, the NASA administrator says, well, you know what? I came in here thinking that this was the craziest thing that I'd ever heard of, and I still think it's crazy. But I think it might just be crazy enough to work.
No one has ever accused the folks at JPL of lacking confidence. But after the rover's Spirit and Opportunity landed on Mars, the confidence and ambitions went through the roof.
There was a group adrenaline rush throughout the entire Martian community, which was almost like we can do anything.
Spirit and Opportunity were designed to do basic geology. Next time out, they wanted an upgrade. A fully loaded, nuclear-powered mega rover, built to find out if Mars ever had all the ingredients necessary for life.
It's going to carry with it an entire laboratory. We've never done anything like that before. We've sent a few instruments, but we haven't sent an entire laboratory.
You take something that you think you understand and you say, let's do it bigger. Let's make it 5, 10 times as big. Now you get to a whole new realm of complexity that we had never faced before.
Watch our clearances.
This is the biggest spacecraft we've ever built. Everything is supersized. It comes with all of the pleasures and pitfalls of something that big. We have a new landing system because of the size of the vehicle. We've got an instrument package that's much more complex. It makes everything more complicated.
They're building 2 rovers at the same time. The one that will go to Mars and an identical twin for hard testing on Earth.
It has to work reliably 100 million miles away from us, and so before we send it, we test the bejesus out of it.
Today, they'll simulate a key event in the landing sequence. The violent jolt when the rover's mobility system drops into place.
We're going to do our final countdown and then we'll test.
The wheels are off to reduce weight, simulating Mars gravity, less than half what it is on Earth.
Verify everyone is in a safe location. 3, 2, 1, fire.
And so there it is, and this just beast is sort of jostling around. We were asking ourselves, what have we done?
Since we have a very large spacecraft, we need a really, really, really big parachute. One of the most difficult things to do is to test the strength of the parachute. We had to go to the world's largest wind tunnel in order to accommodate this big of a parachute.
The chute has to survive opening at 900 miles an hour on Mars. On Earth, where the atmosphere is 100 times denser, they can generate the same force at 90 miles an hour in the wind tunnel.
Armed. 3, 2, 1, fire. Good shoot.
It was too easy. It was too easy.
We thought we'd just, go to the wind tunnel, we'll run our tests and check the box. But parachute testing is never without its surprises.
Passing 50 knots in the test section.
The next day, test number 2. The same kind of chute at a higher speed.
On my mark. 3, 2, 1.
Bad shoot. Oh.
We have an e-stop. Stand by, everyone.
We really had no idea what was going on here. It was just a total tangled mess. I mean, it was frightening.
It was busted up pretty good. Lots of little pieces.
Smaller versions of this parachute have been tested and flown on Mars many times before. They never did this. But a smaller parachute is not an option.
I have nobody to blame but myself, and all of us who sort of formulated this are like,
We were truly baffled. And so we spent months trying to figure out what had happened, why it happened, doing all the failure scenarios.
We were asking ourselves, have we run into a real big, sort of a showstopper problem here?
Very asymmetric opening.
The problem is we didn't have enough data. So for the next test series, we just packed the wind tunnel full of cameras.
3, 2, 1, fire.
So we shot it out, hoping, okay, we'll get another failure, we'll see it, we'll diagnose it, and we'll fix it. Problem was, it opened up beautifully. And so, again, we were kind of stuck.
I don't see anything.
They have to catch another failure on camera to understand what happened and whether it could happen again on Mars. 16 months before launch, they're still trying and running out of time.
5, 4, 3, 2, 1.
Yeah, baby. That's it, buddy. Adam, please try to sample it. That's all we need.
Cool. Okay, wait. Oh, now step it back and let's go frame by frame.
Slow motion reveals the culprit.
When you open the parachute, sometimes the front edges of the bag overlap before it starts to fill and start to turn the parachute inside out.
It's right there. You get a little piece of fabric which has pulled itself on the wrong side of where you're supposed to go. It inflates and it starts to pull the parachute through.
And unfortunately, it starts to tear itself apart. It rips to shreds in the wind tunnel.
The problem is the amount of time it takes for this big chute to open. With the air moving at 90 miles an hour, it takes 10 times longer to inflate in the wind tunnel than it will at 900 miles an hour on Mars.
On Mars, we're vulnerable for less than 1/10 of a second. They just don't have time to misbehave.
We concluded that the phenomena that we see at Earth is not going to happen at Mars. Earth and Mars are different. We can never test a parachute exactly as we'd like to. And that anxiety will be plaguing me on landing day. There will always be this residual nagging risk that some difference could be our downfall.
It's not enough for Curiosity to land safely on Mars. It also has to land in the right place. With orbiters, scientists search for minerals that formed when Mars was wet and may have been suitable for life.
We're looking for habitability. A habitable place has the stuff that life needs. Doesn't mean that life is there. Just means that everything that life would need is there.
It means water. It means a source of energy for microorganisms to live, and it means availability of carbon, which is the building block of all life as we know it.
We know there was water on Mars. We know there's energy from sunlight. So far, we haven't found the organic carbon, even though it's common in meteorites and space dust.
It should be there. All this organic material from outer space is coming down onto the surface, but we have no observations of organic material on Mars.
Harsh conditions on Mars may have destroyed organics at the surface. So Curiosity will have a drill to sample rock below the surface. And inside the rover, a powerful miniature laboratory called SAM, Sample Analysis at Mars, will search for organic building blocks of life.
If we could detect any organic carbon on the Mars surface, that would be a huge discovery.
Everything will depend on being able to drill rocks and deliver samples to the rover's laboratories, none of which has ever been done before.
This is all stuff that's new, and it's complex. And when new things permeate the entire design, the risk goes up very, very rapidly.
With 10 science instruments, 17 cameras, 2 computers, a robotic arm, and 33 electric motors to make everything go, Curiosity will have a huge appetite for power. At night, a 110-watt nuclear generator will recharge batteries that provide power during the day. But Martian nights are cold, 100 degrees or more below zero. By morning, the lubrication in the motor gearboxes, called actuators, will be frozen stiff. They'll have to spend some of the stored power to heat them up before they can do any work.
Now, we thought that we could build actuators that didn't need to be heated. And that's technology with titanium gears and dry lube. Not liquid lubrication, but dry lubrication. And when we built them up and tried them out, they were great. The one thing we didn't do in time was a life test, where you just ran it and ran it and ran it and see whether or not those motors would last for 2 Mars years of driving.
We're in the middle of a life test, and something doesn't look right. Okay, well, let's do a health check. And during that health check, you hear, and you're like, oh no. And then you pull it apart, and there's dust everywhere, and the gearbox is eating itself up.
The combination of the lubrication and the titanium gears and the whole design, it just wasn't going to work.
They have to start over from scratch with a new design for all the actuators. A serious blow to the schedule. Without motors, the rover is just a box full of wires. There's no drive system, no robotic arm or camera mast. No moving parts at all, and no way to test anything. And that's not the only problem. The rover electronics and computer systems are all new and unproven. The software for everything from landing to rover operations on the ground is running more than 2 million lines of original code.
I'm used to high-pressure schedules, but we have a lot to do. People think that this might be easier than it is. It's not. It's very hard.
The launch deadline is just 12 months away.
Mars is coming, Mars is coming, Mars is coming, and that, you know, your launch date is set.
As they orbit the sun, Mars and Earth line up close enough to launch a mission just once every 26 months. Miss that chance, and the next one is another 26 months away.
So we've got guys coming in at 4 in the morning, working till 11 in the morning, coming in at midnight, working till 4. I mean, it's full court press right now.
We were really on schedule to make it. working 24 hours a day, 7 days a week, turning out actuators, making sure that everything tested, flight ready, ready to go.
Then a new problem. Something is binding inside one of the actuators. It's fixable, but it means that every one of them has to be taken apart, inspected, put back together, and retested.
We knew that was well more time than what we had.
We had trouble with the actuators. We had trouble with the energy problem. We had trouble with the electronics. All these things combined to a story where it just was not going to make it.
Running out of options, NASA decides to postpone launch from 2009 until late 2011.
We'd really like to slip 6 months, but our opportunities don't come like that. We have to slip 26 months. It's disappointing. I mean, we'd be launching in a few months. Having that a couple more years out is hard.
In the summer of 2010, 16 months before the new launch deadline, Curiosity is back in action.
I'm feeling a lot more comfortable, but a lot of things can still go wrong. My goal is really to get to the point where I can sleep at night.
We don't actually know what the surface is going to look like. And so you try to imagine, okay, what's the worst case? And that's what you have to design for. You always have this sort of optimistic skepticism as an engineer. You're always hoping that you're out of the woods, but you go to sleep and you don't sleep.
I don't sleep through the night, every night, or any night.
Today, they'll test the final unspooling of the rover from the sky crane just before touchdown.
This is the test where we're checking it out. And it is gut-wrenching just from that point of view, because you realize how complicated it is and how much stuff is actually going on.
If we don't have this right, whatever, we should all go home.
We are armed. Test is commencing in 5, 5, 4, 3, 2, 1, fire.
Good so far. But after touchdown, the sky crane has to take up the slack in the cables before it disconnects. The cables begin to retract, but one of them, an electrical cable, suddenly stops.
We have a leash, a little spring and a little line that picks up the slack on the umbilical, that electrical cable. And that leash was doing a good job for a while, but stopped picking up the slack. And so you see some of that electrical cable is on top of the rover. We don't want that because it could have laid over and snagged on something, and when we go to fly the descent stage away, we could be stuck. Down near the bottom.
A piece of cord on a spring could be the difference between success and failure.
First glimpse of actually seeing the cord through that hole.
Can we just zoom in there just for a second?
If the leash got jammed in the mechanism, it could be a design flaw that would set them back months. But it might be something simpler.
Okay, wait, gentlemen. What's our force margin on Earth here?
Well, this thing is very marginal on retraction force here on Earth.
They suspect that the spring is not strong enough to handle the weight of the cable in Earth gravity, where it's twice as heavy as it will be on Mars.
Reach in.
But they have to prove it.
We're in that part of the project which is like the red zone. Our world is full of infinite detail and a lot of paranoia and worry.
You're down 2.0 right now.
It takes another long night to prove that the problem is, in fact, the weight of the cable in Earth gravity.
Moving, moving.
It's moving freely, so it's a cable mass issue.
Tom looks like he's ready for a bottle and a...
What's involved if we were to...
And I'm ready for a bottle of myself.
After 5 years of deliberation, the scientists have settled on Gale Crater as the landing site, a basin 100 miles across with an 18,000-foot mound of layered rocks in the middle. Those rocks could tell the story of whether life ever had a chance on Mars. Curiosity will climb the mountain and read the layers like the pages of a book.
This becomes a mountaineering expedition. This is a place where we could go for 10 years.
With 5 months to go, the entire operation moves to Florida to prepare for launch.
Everybody has invested a lot of time and energy into this. And we're talking about thousands of people. It's a monumental effort, but that's what NASA does. We all want to know, could life have ever existed on Mars? This mission is not going to be easy. It hasn't been easy, but we want an answer and we're going to go get it.
Eight years of work have come down to this: a $2 billion spacecraft sitting on top of 1 million pounds of rocket fuel.
On the numbers, launch is pretty scary. You know, they give a 99, 98% probability of success on a launch, which is about what we're giving on our probability of success at landing. So we're going to push the go button, and if things don't go well, we're all in, and our whole investment will be lost.
The planets are aligned. It's time to go to Mars.
NSC, spacecraft to internal power. Roger. Perform launch on time verification.
Roger. Launch enabled.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Main engine start, 0, and liftoff.
It's gone. It is gone.
That's it.
It's on its way.
Eight months later, Curiosity is on final approach to Mars.
I don't think anything can really prepare you for a night like this. We're all trying to remember to breathe.
We have everything riding on this. Everything.
Three-stage separation. We are standing by for
Started guided entry.
The vehicle is on its own. We have no more commands to send. If it's not going to land safely tonight, that mistake was made ages ago.
30 seconds to entry.
It takes 14 minutes for signals from Mars to reach Earth. So the spacecraft follows the script as written, line for line.
Parachute deployed.
Each person has their own thing to watch, but there's nothing we can do. All we can do is hope that we didn't forget something.
We're down to 90 meters per second at an altitude of 6.5 kilometers per second.
Tingle's Odyssey is still strong.
UDEP is good.
Filter converged and velocity correction. Ground solution equals minus 10.8 meters.
UDEP is stable. UDEP is good. Touchdown confirmed.
Curiosity is on Mars.
CDL, we have data. Things are looking good. ECAM is green. You can see what we think is the rim of Gale Crater. All the image sequences executed successfully. No warning AVRs. Everything is good to go for Sol 1.
Okay, great. Thank you.
The scientists and engineers now live on Mars time, measured in Martian days called sols.
Typically, we come in the morning and we look at all the images that have come down from the night before. We talk about the observations we want to make, the drives we want to do, and then we make a plan for the rover to perform the next day on the surface of Mars.
And that whole science and engineering plan comes together in about 4 hours. And then another 4 hours is spent turning it into computer code before we actually send it up to the rover. So it's about an 8 or 9 hour process every single day.
All right, so this is a good time, I guess, to just remind the theme.
Operations is a lot of work and it can be stressful. But there are some days when you actually take a step back and you realize, oh my goodness, this is Mars. And that just kind of blows your mind.
Curiosity is in Gale Crater to find out if it ever had the conditions and raw materials for life. Orbiters have seen evidence of rocks that formed in water in the foothills of Mount Sharp, about 10 miles from where Curiosity landed. It could take a year or more to get there. But they also see a channel, possibly cut by water through the crater wall, with a fan of sediment below, not far from the landing site.
When you're a mission that's chasing evidence of water and ancient lakes and rivers on Mars, this is the kind of thing you're looking for.
It's just a few hundred yards from the landing site to the basin they call Yellowknife Bay.
All of a sudden, we see this huge expanse of flat, smooth rock. Nothing ever like it on a landed mission before on Mars.
Exactly what you would expect from sediments in the bottom of a lake. That means it's a good place to collect the story that we're after. So we're in Yellowknife Bay, and Curiosity drills the first mudstone.
All right, folks, our first hole on Mars, big success.
And when the pictures came back, what we saw was gray. And it hadn't been rusted out, like everything you see all over Mars. Red stuff tells us the story we're looking for has been erased. When we get to the gray material, there's something still left. Not all of it has been destroyed.
The first sample goes to an instrument that uses X-rays to identify minerals. What it found was clay, a mineral that forms in water.
And there wasn't just a little, it was 20% of the rock. And that indicated not only that a lake existed there for some time, it was fresh water. It was a kind of water that life would be able to thrive in.
So here we are investigating the rock record of a freshwater lake some 3 billion years ago. what about the organics?
The SAM laboratory searches for the organic building blocks and other chemical necessities of life. It heats the sample and pipes the gases to instruments that identify the components of the rock.
When the first sample came back from SAM, we found a lot of the basic elements that life requires: carbon and oxygen, hydrogen and nitrogen. What we didn't know was whether there was any organic molecules.
Organic molecules are carbon compounds that form the physical building blocks of life. They're easily damaged by radiation and chemical reactions, which makes them hard to find in billion-year-old rocks, even on Earth. It's even harder on Mars.
We're looking for organics, and it was tough. It was tough to find things because it's got this stuff in there called perchlorate. And when you heat it up, it goes poof.
So we're making a little bit of Mars here with some organic matter and some perchlorate, which we find all over Mars, but is also used in explosives and fireworks. This is what happens when we put it in SAM. We heat the sample up.
We realized, hey, there's all of this perchlorate there, and it's combusting the organic material that might be there. That SAM oven had become a reactor of all sorts of chemistry, and we didn't understand what that chemistry was.
By now, pressure is building to get on the road to Mount Sharp.
That's, getting to be almost a year into the mission, and we hadn't really moved more than half a kilometer from where we landed, and Mount Sharp was still way in the distance. And so we just had to pack things up and move on.
They have to find a way through the massive dune field that lies between Curiosity and Mount Sharp.
The Bagnall Dunes run east to west along the base of Mount Sharp. They are several stories tall and not something that the rover can just drive up and over. So we had to drive miles along those dunes to find a way through and start climbing the mountain. The clock was ticking, and we really were trying to book it to the base of Mount Sharp.
Curiosity is a powerful machine, but it's not fast. 80 to 100 meters under the best conditions. Top speed on this drive will be even slower than that.
We can see some dents in the right middle wheel. Ah, okay, that's interesting.
Just as we're leaving Yellowknife Bay and we're, putting the pedal to the metal and aiming for Mount Sharp, we start realizing that the wheels are showing a lot more damage than we expected.
So you can see features like this hole here. We have a lot of dents, we have a lot of scrapes, small cracks. And so this was pretty early on in the mission, and you can see we already have some pretty big holes in the wheels.
The mobility engineers run tests to see how much more life they can expect from the wheels running over different types of rocks. Eventually, they'll upload software to adjust wheel traction over the roughest ground. But for now, the solution is proceed with caution.
We had to pay a lot of attention to all the individual rocks that we might be driving over. So that slowed us down a little bit.
For the rest of the drive to Mount Sharp, they try to dodge the roughest terrain, searching for routes that are sandier and softer, but not too soft.
From the day we left Yellowknife Bay, we were just driving as fast as the wheels would allow, 7 days a week, just to get to Mount Sharp. And it took us the better part of a year to do that.
Nearly 2 years after landing, Curiosity is approaching the base of Mount Sharp. Along the way, it's seen clues to the origin of this 18,000-foot mountain.
As we were driving across the plains towards the mountain, we came across these very flat sandstone slabs, slightly tilted, and all facing the same direction. we realized that what we were likely seeing was an ancient delta, a place where a river encountered a lake. But the remarkable thing was it pointed towards the center of the crater, the place where there's now a mountain. It didn't point to a big hole in the ground where a lake might have been, but a mountain that we realized might itself be composed of the lake beds.
More clues turn up when Curiosity finally reaches the rocks that form the base of Mount Sharp in the Pahrump Hills. It turns out to be mudstone, a lake bed, as predicted by the delta. Drilling again, they sample 3 new sites, but the signals are still hard to read.
It was a puzzle. What is in this sample? Where are the organic molecules? There was a lot of work to be done to pick the data apart and understand it.
After 6 months, it's time to move on again. Curiosity still has miles to go before it can turn south and start climbing straight up Mount Sharp. They're headed for a break in the dune field that's been blocking Curiosity from the mountain for almost 3 years now. The route winds through a landscape of towering buttes spotted from orbit years before landing.
And all of a sudden you're there, and you're like, my God, where are we? Look at where we are.
Then, finally, they're out of the buttes, through the break in the dunes, and up the face of Mount Sharp.
And when we finally made that turn to the south and we really started climbing the mountain, that felt really good.
The mission was really going in full swing. We were at the mountain, we were making great progress, drilling holes left and right. And then one day, the drill did not execute as commanded. It was the first time I really felt that this all could quickly come crashing down.
Working properly, the drill braces itself against the rock with stabilizing posts. Then a separate motor drives the drill bit into the rock. But now, that motor is not working.
Every day that went by that we couldn't drill was a huge impact to the science mission. So we were working as hard as we could to try and get this capability back.
The prospect of never drilling again really changed the mission for me. I had to be optimistic that it would work. But man, when the whole mission is riding on that, it's tough.
Without the feed motor, they'll have to use the rover's arm to push the drill bit into the rock without breaking anything or getting stuck. Something it was never designed to do.
We all realized that this wasn't going to be an easy fix. This was going to be months and months of work.
The loss of the drill does have an unexpected benefit. It leads to the discovery of the first complex organic matter ever found on Mars.
And instead of continuing to process new data as we would if we had the drill, we said, okay, let's go back and look at the old data. And that's when we found the organic molecular signal.
With time to dig deeper into the data from Pahrump Hills, Jen Eigenbrod is able to see past the effects of the combustible perchlorate.
And it took a lot of mathematics, analyses, but eventually we found it. We're seeing organic carbon, ingredients for life. This drives our search for life on Mars.
That could include life on Mars today. Curiosity has also detected methane in the atmosphere, a gas produced by life on Earth, but also by geology. The source on Mars is still a mystery.
We just don't know. But we can go back to Mars with other missions and try and pick that question apart.
Since leaving the crater floor, Curiosity has found more clues to the origin of Mount Sharp.
We've driven up over 300 meters vertically on Mount Sharp. And we've seen millimeter scale layers laid down by ancient lakes, thousands and thousands and thousands and thousands of them, built up this mountain that's kilometers high.
What this is telling us is that the lake or the lake systems that were present here lived for a very long time. And the more we climb and the more we continue to see evidence for the lake, the longer it had to have been around.
So Gale Crater had lots of liquid water, had the raw materials of life, sources of energy, and all those things existed together in the same place for millions, if not tens of millions of years. This tells us that Mars, as a planet, was a friendly place for life for a long time in its early history.
Big day today, folks. Indications are that this was a successful sample acquisition. We did it. Let's take a look at the image.
Finally, after 18 months of work, the drill is back. The engineers have hacked into a force sensor in the robotic arm, giving Curiosity a sense of touch. Now it can push the bit into a rock the same way a human would use a hand drill. In June 2018, they deliver a new sample for the first time in a year and a half.
It's been a tough road, but we've reinvented how the drill works, and we're back in business sampling Mars.
From its perch 1,000 feet above the crater floor, Curiosity looks back on its journey. And back in time when Gale Crater was a lake that could have supported life. Still to come, the story of how Mars changed and became the world it is today.
The plan we always had for Gale Crater was to climb that mountain, rock layer by rock layer, and basically read the ancient history of Mars, from a wet planet to a dry planet.
Yeah, we got a whole mountain to climb still. We've gone up a lot of it, but we have a lot more to go.
We've been on Mars for 6 years. It's not the same old, same old. Every day is special. I will forever be absorbed in that.